Hi everybody, and welcome to a very quiet Tuesday morning in Mount Rainier National Park. This is another road, this one, the road up to Paradise, and we are approaching from the east. So I'm using the Pat Pringle Roadside Geology book backwards, following the mileage, working our way to the west up to Paradise. This cute little tunnel and this outcrop of Stevens Ridge Formation is brand new to me. And hopefully, if we play our cards right, by the time we get up to Paradise, the low clouds will burn off. You might be able to see some blue sky up there. I mean, I know Rainier is out because I saw it from Ellensburg this morning as I left the house at 6 a.m. Maybe by the end of this video, the mountain will be out. Thanks for joining us. We continue learning new things about the olden days of the Cascade Volcanic Arc, going back 46 million years. Thanks for joining us. Let's get started. A look up Stevens Canyon, and you're like, I don't know where I am. What's going on? Well, I barely know where I am, but look what I brought. I forgot I had this thing. These cute little plastic relief maps that were all the rage a generation ago are still very, very handy. Good morning. So we're going to get a lot of use out of this thing. And even though the title of this thing is Mount Rainier and it was produced in 1983, we have St. Helens with its top blown off, Mount Adams. But if we zoom in and fly our drone approaching Rainier from the south, you can see the video we did last time and the video we're doing today. Last time, I crossed up and over Chinook Pass down to Cayuse, worked my way north on 410, got onto the Sunrise Road, and you can see the Sunrise Road right here. And you might remember my green chair sitting out there looking at Rainier, but I was to the northeast of that. So that was the last video. Today, we are down here, and I entered the park using my free pass, no big deal. In the clouds, crossed Backbone Ridge, and we're someplace in here now, in Stevens Canyon. And we're heading towards Paradise Visitor Center, which is kind of in here. Okay, clouds are starting to break up. I think there's a good chance we're going to see Rainier soon. But today we are on the southern portion of Mount Rainier National Park, Backbone Ridge. And we've got colors here that we have not dealt with yet in this little series of field videos. What's the purple? What's the pistachio green? This is Ohanapecosh, remember? This color and this color. So Stevens Ridge Formation is the pistachio green. Rhyodacite, rhyodacite ash flows. Lesser amounts of volcanic breccia, sandstone, and siltstones of epiclastic and pyroclastic origin. Tunnel through welded tuff. The Stevens Ridge rocks preserve an example of the scale and nature of some of the volcanic eruptions during the early Miocene in the southern Washington Cascades. The thick welded tuff layers were deposited by ash flows that originated in large eruptions of ash and lapilli. The flows moved as sheets, yards or tens of yards thick, flowing outward from the vent. These pumiceous flows were hot enough and thick enough in some places to weld together after they came to rest. So here and here. In such eruptions, several to many tens of cubic miles of volcanic debris may be injected from the magma chamber fueling the volcano, so much that part of the volcanic edifice falls into the void left behind, creating a caldera. The welded tuff is visible in the next mile or so. Okay, well, wow. How about that for drama? Got the key in my pocket. Nice and quiet. Look both ways before crossing, boy. This is the Stevens Ridge, full of welded tuff. Well, what do I notice? What do you notice if you've been following along with these programs? Well, it's not green, right? It's not the green, the consistent green of the Ojanapakosh. And yet again, we can see that there's all sorts of drama inside of these volcanic units. This is a welded tuff, and I think it's the scale. I'm going to have to work hard to get my mind around the scale of this Stevens Ridge welded tuff. But there's so much of it, it's so thick, that parsing out or trying to visualize the scale of the explosive events back in the Miocene, I don't know the date yet, it's worth thinking about. But we are younger than the Ojanapakosh Formation now. Yeah, just if I zoomed by and I didn't have the Pringle guidebook, I think I would be looking at a Pluton, like it's real light colored. But that's not the case. I mean, it kind of looks, this texture as a rookie, like I am, looks similar to the Ojanapakosh, but I don't think we're at sea level anymore. I think, in fact, I'm almost sure of it. And if we're in the roaring 20s with this Stevens Ridge, which I'm not sure that's true, but then what's the elevation and where are the vents for these truly impressive, colossal explosions? I mean, you gotta love these tunnels. I mean, you can do what you want, but a tunnel built into Stevens Ridge. Yeah, every chunk. Pyroclastic flow. I think something like this, and there's hundreds of these slabs, right next to this tunnel on the Stevens Canyon Road. I think this is what we should have in mind for our pyroclastic flow deposits, our ash flow tuff deposits of the Stevens Ridge Formation. I'm just getting started. I don't really know how excited to get. But just the fact that we have a light colored unit that's got all these broken shards, pretty sweet. Mid-September in the Cascades. You gotta love it. Okay, there's an outcrop just up ahead that I don't know much about. Let's read first. Pat Pringle says, pull out with an outcrop of platy Mazama Ridge andesite. Mazama Ridge andesite. Right over there. Sisson and Lamphere dated the Mazama flow at about 90,000 years old, and they show that the age and the chemistry of the flow are similar to those of the Bench and Stevens Canyon's flows of Fisk and others. And further, that these flows are actually all part of the same flow. Okay, I don't get that, but whatever, let's go over and take a look. And you're like, no, go over there, I want to see the cone. Oh, come on, man, that's quaternary stuff. That's what everybody's into. We're not like everybody. We're interested in the stuff that most people just blow right by, including the Mazama Ridge flow. I didn't even catch what kind of lava it is. Is it andesite? Is it something else? I will learn, but let's give you a look at it. Oh my God, this morning is just really amazing. So, yeah, we're losing the mountain now. You know how that goes. The lighting comes and goes. The cloud cover comes and goes. Well, it's true. This thing is platy. Focus. What kind of lava does that look like to you? I don't see any hornblends. And hornblends are black minerals that are typically long and thin. I do see a few little black minerals. I think those are little biotites. I'm going to continue to work with igneous petrologists. Timber! And they're going to be able to help me. But yeah, this flow is unique. And what did Pringle just say? Tom Sisson thinks that this is the same thing as the Stevens Ridge lava. So we jump from the early 1960s to the late 1990s, and we have abilities to get chemistry and dates that we couldn't get back in the 60s. But what does this lava tell us? I mean, we're definitely in the Ice Age now, so I guess I'm not that interested now that I think about it. But to be thorough, if I'm doing a video on the geology along the road to paradise, I guess I need to dip into the Ice Age once upon a time. Okay, we're about to get out and look at some Tatoosh Pluton at Sunbeam Creek. But let's catch our breath here. It's such a perfect morning. It's a pleasure to be with you. If we go back to the OG paper by Dick Fisk in 1963, Johns Hopkins University, Geology of Mount Rainier National Park, this document is now at nickzentner.com. Click on the word Cascades in the upper right hand corner. You'll get to it for free. Not only this paper, but this map as well. This beautiful, beautiful map of Mount Rainier. And yes, we are approaching paradise, and we are up in this area now by there's Sunbeam Falls, Reflection Lake. I can't read some of the other stuff. But we're in this vicinity here. But I think before we lose it, and I'm starting to lose it a little bit, if we look in the Fisk paper, here's a very humble, simple figure, and it nicely summarizes what we've been doing thus far with these Mount Rainier videos. I have been really into the Ohanapikosh Formation, and I think today we pushed 10,000 vertical feet of thickness of the Ohanapikosh up to 15,000. 15,000 feet of Ohanapikosh Formation, the greenish stuff, which we're not looking at today. But there's an unconformity question mark, and then Fisk back in '63 says, yeah, that we have this Stevens Ridge Formation, which we were just looking at the towards the beginning of this video, rhyodiacitic ash flows, volcanic breccia, sandstone, siltstone. Yeah, and then that sits below the Fife's Peak Formation, which I've done very little with so far. And I think modern geologists, in other words, geologists today, are not into the Stevens Ridge. They feel like the Stevens Ridge is just a local story in Rainier Park. And instead it's the Ohanapikosh and I guess the Fife's Peak that are laterally extensive through much of the Cascades. But that's a working set of ideas. But what we're about to go out and look at is the Tatoosh Pluton. And let me flip you around. Pleasure to be with you. I'm having a blast doing these videos with you, so thanks much. One of the earlier videos you saw, perhaps you've been watching these field videos in order, was the Tatoosh Sill. Do you remember that big fat orange thing exposed between Chinook and Cayuse Pass? And I was wondering out loud, it's not staged by the way, I truly am like learning as I go, as I film. I was wondering if the Tatoosh Sill was connected to the Tatoosh Pluton. And the answer is yes. But this is our first chance over at Sunbeam Creek here, south of Rainier's Cone, to get a good up-close look at the Tatoosh Pluton. I don't know what it looks like. But I found a paper that I printed out last night that I brought along this morning by Jim Mattinson, father of Chris Mattinson, who I work with at Central Washington University. And if you recall in the sunrise video, again, these are in order. If you recall in the sunrise video at Rainier Park, Fisk and others in the early 1960s were asking, is it possible that all of these Plutons in the area, the Tatoosh Pluton, the Spirit Lake Pluton, the Snoqualmie Pluton, are they all part of one big blob? Are they all exactly the same age? And in 1963 they said, there's no way for us to know that, but we wonder. Well, Jim Mattinson's paper says, no, they're not all one major Pluton. And here's his paper. Flip you around. Emplacement history of the Tatoosh volcanic plutonic complex, ages of zircons. Now, Dr. Mattinson was a pioneer with the zircon geochronology that Mike Eddy and many others are using today. Let's read the abstract together. 1977, the Tatoosh volcanic plutonic complex, exposed in and around Mount Rainier National Park, is one of a series of igneous bodies that are exposed along the axis of the high Cascades. It is possible that these tertiary bodies are the eroded roots of an ancestral calc-alkaline arc, in other words, ghost volcanoes. The Tatoosh complex was emplaced into volcanic rocks that were evidently oceanic in character. That's like the basalt of Summit Creek and the Ohanapikosh Formation, and even going back further, the Rimrock Lake Inlier. Isotopic ages, here in 1977, of zircons from plutonic, hypabyssal, and volcanic phases of the Tatoosh activity probably were fed by repeated injections of magma from a deep source over the course of 12 million years. The earliest activity was a bunch of dikes and sills about 26 million years ago, and then about 25 million years ago, and again at 22 million years ago, the Tatoosh magma broke through to the surface to form thick, welded tuffs. Magmatism culminated with the rise of the core of the Pluton, and there were two more bouts of activity, 17.5 and 14.1 million years ago. So that's a stunningly dramatic abstract for somebody like me just starting to realize that there's all this spread of ages just within something called the Tatoosh. So if we go to the Tatoosh, Jim says, well, yeah, there's the Tatoosh Pluton, it's 14 million, but it's not just 14 million, right? We had all those other dates, all these other chapters, just with this complex building of the Tatoosh volcanic plutonic complex. It's not in other words, it's not just a bunch of granites. And then he also has been doing, again, Jim Mattinson in the 1970s is collecting samples from the Snoqualmie batholith, the Grotto batholith, the Index batholith, the Squire Creek, the Cloudy Pass, the Golden Horn, the Chilliwack, the Mount Barr. Basically from White Pass up to Canada. And he's showing with his geochronology from zircons and a brand new method that there are wildly different dates for this stuff that just 20 years earlier, 15 years earlier, was suspected to all be the same material. So hats off to Jim Mattinson. Wow, what a paper. And I'm sure there's much more that I'm yet to discover. I'll have to talk to Chris about his dad and get some backstory on that. Doot-doot. So, together, let's lay eyes for the first time with an outcrop of the Tatoosh Pluton. And which of those dates is appropriate right here? Is this the Tatoosh that's 25 million, 24 million, 14 million? I don't know. Aww. For us rookies, the Tatoosh Pluton is a granite riddled with mafic enclaves. No big deal. I think I read it's more like a quartz monzonite, which I don't really remember the technicality of a quartz monzonite. So one of my favorite things here is that this is not just the Tatoosh Pluton as an island. There's a regional story. And the Tatoosh Pluton happens to sit underneath an active cone, otherwise known as Mount Rainier. Morning dew on the legs. Okay, you want Tatoosh Pluton? Let's get serious. No more screwing around. Beautiful outcrop. All of it. And coarse-grained. Quartz monzonite or something else. Granitic.
They got the rock!
Hey! Nice. Let's go over and take a quick look. Pretty simple granite to my eye. Plenty of quartz, some biotite. That's as much as you're going to get out of me. Mm-hmm. Tatoosh Pluton looking south. Tatoosh Pluton in Peach. I'm at Rick Secker Point. I've overshot Paradise now, but I wanted to come down here for nostalgia reasons. I have a family photo from 1979 when I was a moody teenager and we were at Ricksecker Point. But I am enjoying the Tatoosh and the pink, which is one of these andesite lavas that filled a former valley, much like Rampart Ridge. So this is the lava, the andesite of Ricksecker Point. So we're going back and forth between the andesite of Mount Rainier volcano and the granodiorite and quartz monzonite of the Tatoosh Pluton. Toot toot. Let's go ahead and go over and see this contact. That's the peach stuff. The Tatoosh Pluton, which is, I think I'm getting more and more interested in that frickin' thing. Because even though that's majestic and absolutely GD gorgeous, it underlies the entire park, right? Ha! I mean, it is gorgeous and looks pretty damn young, doesn't it? This doesn't go back 20 million years. This doesn't go back 30 million years. This is one of the Ice Age lavas that erupted out of Mount Rainier cone. And I'm sure there are specific dates for each of these flows now. I don't know which date we're talking about, but I just wanted to capture this. Maybe, I don't know, what an ideal spot to teach volcanology. If, let's say, I don't know, you're teaching Geology 478 and you wanted to do a Saturday trip in September. And maybe you had multiple Saturdays reserved and you picked the best weather day and you came up here with Geology 478 and 578 students in the fall. I know. Volcanology is not taught until the spring, but I don't know, maybe because of this kind of set of outcrops, maybe 478 needs to be taught in the fall. There's a radical idea. Monster andesite lava flows, beautifully on display in the national park. So for a change, I'm actually looking at a lava flow. I'm not looking at a frickin' Fiamme breccia or whatever the hell. This actually is lava that you can follow right back to its source. And this is not lava from a ghost volcano, it's lava from a volcano, which is frickin' right over there, man. Amazing. Yeah, I'm starting to get the look now. The pink kind of grades into a dark. Ricksecker Point. Love it. Intra-canyon flows of lava. Andesite, lava. With this kind of pink, I don't understand the pink. Is this pink look weathering? Or is this, I don't understand the pink. Because it seems like the true lava is this dark gray crystal rich thing. That appears to be the story at most places that I can find these andesites of Mount Rainier, but I don't get the pink. Why is it sometimes the entire block looks pink. Sometimes we have this flow banding business. I don't get it. Pink, black, pink, black, pink, black. What's the pattern? Tatoosh, plutonic, granodiorite, peach on the maps. Surface lava, andesite, erupting from Mount Rainier, pink on the geologic map. Damn. Beautiful. And yes, looking at Rainier itself, we can see, of course, worms of glacial ice flowing away from the summit. But if you zoom out, there are worms of andesite of Mount Rainier, pink worms, flowing out that were filling former large valleys. That in itself is pretty sweet, isn't it? The ridges that radiate out away from the active cone are andesite lavas that used to flow down valleys. So today's ridges are yesterday's valleys, and today's valleys are yesterday's ridges. Put that in your pipe and smoke it. You can pass me. And clouds are moving in. Our timing is pretty good. Some beautiful glaciers on the south side of Rainier through the windshield. And just like we did with the sunrise video, once I get to the end of the line, the parking lot, I suddenly lose interest in everything and I get out of there. And I think that's going to be true here as well. So this video, I think, was named Road to Paradise. And so if you need to see all the details of what's available to you at a place called Paradise, you can look for a different video with that. So that beautiful historic building is the Paradise Inn. Rainier in the distance, of course. But on this little one-way road, which exits the very busy parking lots, is a very quiet place and an outcrop. crystal rich lava. Which lava flow is this? Kind of a dark gray ferric lava flow. There's some cute little plates here. Huh. Pretty good looking lava flow full of crystals right here at Paradise. Basically, Paradise Inn is built right on this lava flow. I like this lava flow. It seems kind of simple and pleasing and crystal rich. Is it an andesite? If it is, I think I have a new way to appreciate andesite lavas in a place like this, courtesy of a very important paper by Adam Kent that Hannah Shamloo loaned to me. Oh, this is kind of interesting. We've got a little pink swirly action in between all this lava. So we got these pink things interspersed with this Paradise Inn lava. And the pink stuff is all complicated and kind of gnarly looking. It's almost like there's a violent pink thing happening. Oh no, what? The pink stuff morphs right into this black. Weird. Thank you, everybody. I hope you enjoyed this video from the road to Paradise. It really does feel like paradise on a Tuesday morning in early September. Hope that you continue with these field videos, and then once we get to winter time, starting in early November, online from my office, Cascades Volcanoes, A to Z. Thank you. Goodbye.